comet from another star system is racing through our solar system right now. It might be older than the Sun, its chemistry is strange, and Mars orbiters plus the James Webb Space Telescope are pointing their eyes at it as we speak. You won't see it blazing overhead, but this quiet visitor could rewrite parts of our playbook. Let's talk about 3I Atlas. First, what is it, and why 3I? We've only ever confirmed 3 interstellar objects passing through our neighborhood. Oumuamua was the first, Comet 2I Borisov was the second. This is number 3, 3I Atlas. Interstellar means it didn't form here. It's not from our Oort cloud. It's a traveler from another star's nursery that wandered into the Sun's gravity well and will not stay. How do we know it's just visiting? Its path is hyperbolic. Bound objects trace ellipses around the Sun. Unbound visitors trace open curves and never close the loop. 3I Atlas is on that open track, swinging in, stealing a little energy from the encounter, and heading back to interstellar space. How fast is it? How close will it get? Fast enough that gravity can't capture it, tens of kilometers per second relative to the Sun. Close enough for big telescopes to study its light in detail, but far enough that it's not a naked-eye spectacle. At closest approach to the Sun, it stays well outside Earth's orbit, and its closest approach to Earth is still farther than the Sun is from us. So if you step outside and don't see anything, that's expected. This is a data comet, not a fireworks comet. Now the part that has astronomers buzzing, its recipe. Spectra, the barcode of light, show a coma unusually rich in carbon dioxide. In simple terms, the gas around this object contains a lot of CO2 compared to water vapor. For comets we've studied, water usually dominates once they're close enough to warm up. Here, CO2 appears to be in the driver's seat. That hints at a formation zone that was very cold near a CO2 ice line, or a surface that's crusted over in a way that lets CO2 escape more easily than water. Either way, it doesn't exactly match the patterns we're used to from most solar system comets. How big is it? That's still being refined. Early imaging places an upper limit of a few kilometers across, but the true nucleus could be smaller. Headlines love superlatives, but the honest answer is size estimates will tighten as more observations roll in. Science is comfortable saying, we don't know yet, and then going to get the data. Why don't we just fly a spacecraft to it? Because timing, geometry, and budget all have to line up, and they rarely do for surprise visitors. Interstellar objects show up unannounced and move fast. That said, we can still do something clever. Use in-place assets. Space telescopes can read its spectrum from afar, and spacecraft already orbiting Mars can try to watch it when the geometry briefly favors the red planet more than Earth. Those vantage points let us squeeze extra information out of a target that will never come close to us. Let's pause on the big rumor you'll hear anytime something interstellar shows up. Could it be an alien craft? Right now, everything we see looks natural. There's a diffuse coma and dust. The light signature matches icy materials, especially CO2, with the kinds of traces you expect from a comet. The trajectory is a clean gravity-only flyby, no controlled course changes, no beacons, no anomalies that demand technology as an explanation. It's good to ask the question. It's better to follow the evidence. And the evidence points to comet. Where did it come from exactly? Pinning down a birthplace for a single rock is hard. But its incoming motion may fit populations of older stars in the Milky Way, which raises a tantalizing possibility. We might be sampling ice that formed in a very old protoplanetary disk with a chemistry set a bit different from the one that built our comets. That's not settled, it's an active line of research. Still, it's part of why this object matters. Every interstellar visitor is a postcard from a different kitchen. How do scientists read a comet's recipe from millions of kilometers away? By splitting its light. Sunlight hits the coma and tail. Molecules absorb and emit at specific wavelengths. Instruments disperse that light into spectra. Each bump and dip corresponds to a molecule, CO2, H2O, CO, and so on. Compare the strengths and you get ratios. Track those ratios as the comet warms or cools, and you learn what's buried where and how the surface releases gas. Why is the CO2 so interesting? Because it changes the activation distance. CO2 sublimates at lower temperatures than water, so a CO2-dominated comet can switch on farther from the Sun than we expect if water were the only driver. That affects when we can study it, how bright it gets, and what physical processes, like crust cracking, dust jets, or slow seepage, are likely at work. What about dust and color? Does it have a tail? Even faint comets shed dust when gas escapes, and dust is what sunlight really lights up. The tail shape and color can hint at grain sizes and composition. Small grains push away faster, larger grains lag behind. If we see unusual colors, that could suggest different organics or silicates than we're used to. Again, this is why multiple observatories watching at different wavelengths is so powerful. No single instrument sees the whole picture. Okay, but why should anyone who isn't a comet nerd care? Because interstellar comets are ground truth for planet formation beyond the solar system. We can infer a lot about other disks from exoplanet surveys and telescope images, but an object like 3I Atlas is a physical sample, no return capsule required. Its chemistry tells us which ices were abundant where it formed. Its activity tells us how those ices are layered and sealed. Its motion hints at the dynamical chaos that kicked it free. All of that feeds into better models of how any planetary system assembles worlds. There's also a bigger story here. We are entering an era where these visitors might become routine. As sky surveys get deeper and faster, we'll catch more interstellar objects earlier. Some may be rich in CO, some may be water-heavy. A few might even pass close enough for dedicated missions. Each one is a data point in a new science of galactic archaeology, reading the history of other suns from the crumbs that drift between them. What happens after 3 Atlas leaves? It goes back to the dark, trajectory altered by a tiny amount, but still unbound. The datasets stay. Spectra, images, light curves, upper and lower limits. Over the next months and years, teams will reprocess and reanalyze those data with better calibrations and fresh models. Papers will argue, numbers will move. That's the good part. The first draft of VOR, the story rarely matches the final chapter, and science gets better every time we sharpen it. If you've watched this far, you now have the quick answers when someone asks, what is 3I Atlas? An interstellar comet on a one-time pass. Can I see it? No, it's faint and far. It's for big scopes. What's weird about it? A CO2-heavy coma compared to most comets we know. Is it aliens? The data say icy and natural. Why does it matter? It's a sample of another system's chemistry drifting through ours. I'll keep this description and the pinned comment updated as new observations land, especially any results from space telescopes and Mars-based assets. If you want more deep dives like this that cut through hype and stick to what the data actually say, tap subscribe, drop a question below, composition, origin, or how we could intercept the next interstellar visitor, and I'll build the next episode around the top vote. Thanks for watching, and clear skies.